day. In today's video, we'll see how we can run residual phase noise measurement using Keysight's N5511A phase noise test system. What I have here on the screen is the interface out of the phase noise test system. But let's take a step back and look into some hardware connections so that we can run these measurements. So in this video, we'll look at running residual phase noise measurements using two channels with a single sideband calibration option. To do that, we actually need a phase noise measurement interface, what we call a PNMI. On the screen, you can see a 26 GHz version of it. So let's just go through some of the ports we have here. You have a cal-in port on the left, and that would be the port that would provide the calibration, the single sideband spur calibration. Then we have the stimulus in, and this would be your PSG. In this video, we'll use it as a device under test as well. So instead of having a dot here, we would just connect a cable between the two dot and from dot. Next, have channel 1 and channel 2's reference out. This would be connected to the LO ports of the phase noise test system, shown here in this dotted block on the right. And last but not least, you have channel 1 dot out and channel 2 dot out ports that will be connected to the signal or the RF ports of the phase noise test system. So let's look at this again in a simplified block diagram. This red block here is the PNMI. Well, technically the signal generators are outside of the PNMI, but these are the ports that will be connected to the two signal generators. So I will keep the stimulus as PSG. You don't need a PSG as the single sideband cal-in port, but I do have another PSG, so that will be PSG number 2. I do have a cable just connected between the to and from dots. Now the dot out ports from the PNMI are connected to the RF in ports of the PNTS. The LO ports are connected to the channel 1 and 2 reference out. So this is what it looks like physically. So the PSG on the bottom here is my PSG1 or my device under test. PSG2 will then provide the cal-in signal. So that's to the first port, and that's the stimulus is to the second port. I have a cable connected from that to that. This and the two ports in between are the LO in ports to the phase noise test system. So you would want to connect this first ideally, as they are sitting below the RF ports on the phase noise test system. That would just make it a little easier when you're connecting them in. Now, before we can run the measurement, you will have to run a calibration using the single sideband spur. We will look into how we set this up in the user interface in the next bit, but just to highlight what we have here from the previous slide, you would tap out the channel reference out port. So the ports here, instead of having them connected to the RF port of the peanuts, you would take either one. So you can take either from channel 1 or channel 2 and connect it to a spectrum analyzer. I have a Philfox here. You don't need to use a Philfox. You can use any other spectrum analyzer. And as long as you are able to measure the offsets based on what you've set in the measurement definition, then that will be good. So for this case, we are looking at a carrier frequency of about 200 megahertz. So that's where my center frequency is. And I have set an offset of about 10 kilohertz. So using a delta marker, I can say that's 10 kilohertz. And we want to adjust the spur to at least have 42 dBc gap. It can be lower. So that would wrap up our block diagrams. So when we're running the calibration, first, just turn on the stimulus and you would turn off the signal of the single sideband cal port. And when you're asked to apply modulation, you would turn the RF power on the PSG2. All right, so let's now look into the phase noise test system. So when you first turn on the N5511A phase noise test system, this may not be booted up. So just double click on the user interface here and you'll be prompted with the screen. Let's see if I can maximize this so that's a little clearer. So the first thing you would want to do is hit to define, click on measurements. We're not running absolute phase noise, we're running residual phase noise measurements. So let's click on that. And we'll then adjust the offset values. So I have 1 Hz up to 160 megahertz offset values. I'll just keep this as is. We are doing a dual channel, so just make sure you take dual channel. Then we'll go ahead and move to the source. So I want this to be at 200 megahertz. So let's change that. And I'm starting off with about 12 dBm of source power. I'm not measuring any multipliers or frequency converters here, so I'll just check that the detector input frequency is the same as the carrier frequency or the output frequency of the DET, and there's no multiplication factor. I would just keep this as 1. So you can change this if this is not the case, if you're looking at frequency converters, doublers, and so forth. So now we'll move along to the calibration tab. We would want to then take derived detector constant from a single-sided spur. We will keep the rest as is, except for the known spur. As I've mentioned in the slide before, we will keep this at minus 42 dBc at 10 kilohertz. We don't need to apply the anti-correlation connection, so I can now leave this as is. I'll leave the spurious signals. So I just want to make sure this is phase shifter. We're all using manual, and that's an automatic detector selection. You can't change this if you're looking to use other phase detectors. Test set, that's internal. We'll keep it as is. And for the graphs, I would just change the residual so that we know what it is we're doing. And that is it. So now that I'm happy with this, we can go ahead and hit measure and do new measurement. Just very quickly before that, you might want to take not to automatically clear the graph. If you like it to just stay, which I would like to, as if I like to do is comparison. And I just want to make sure that pause at connect diagram so I can see what my test setup is like. So let's hit on new measurement and we'll say yes. As you can see, it'll tell me now it's 200 megahertz. That's a typo there. You can fix that later. So during my measurement, this is my setup. The stimulus will go through my DUT. In this case, because I am measuring the signal generator, this is just a cable. You want to be mindful on the length of that cable based on the carrier frequencies and the wavelength so that you don't go over it, or at least you have enough cable lengths to establish quadrature on both channel 1 and 2 detectors. Okay, so we're satisfied with this. Let's hit continue. So it asks me to apply modulation on carrier signal. This is when you will turn on PSG2. So let's go ahead and do that. So you can see what's happening at the bottom of the screen. It's telling me it's calibrating and it's applying a few things. So now it says remove modulation from carrier signal and connect the DUT. So we'll turn off PSG to RF power. And now connect the DUT if you have one. I'm just gonna connect it across. So now I'm done. I'll hit continue. And now it'll ask me to establish quadrature manually on channel 1. Why is that? If you notice, we're reading about 0.003 volts. We ideally want this to be as close to 0 as possible. If you could hit LS001, it should then stop complaining. So to do that, if you remember what the PNMI looks like, let me bring that up. You'll be rotating the knobs here on the smaller knob. You see this and the small knobs. This is for channel 1 and this is for channel 2. We will rotate them to get the voltages as close to 0 as possible. So let me go ahead and do that. You should be able to see the voltages moving along. So if you could just give me a minute here, we'll go ahead and play around with this. So if you can see, I'm just tuning this down, getting close. And that didn't quite get down. All right, let's try. And it's doing the measurement right now, which is great. And now it tells me it's done. So let's just try to auto scale this a bit. And as you can see, this is fairly good as we are down to minus 180 at the 100 kilohertz region. Let's put some markers on. To do that, let's right click on the graph, put view markers. I can then change this around. With 10 hertz. Let's add a bit more here. Want this to be tone. And there you go. So this is how we can run residual phase noise measurement. I hope this video has been helpful. Thanks for watching.